in today, but most of all, we appreciate Dr. Omosebi for joining in and making the time to talk to us about this important topic. Now, I'll go ahead and give a bit of an introduction. Specifically, Dr. Omosebi is a research scientist in the Energy Geosciences Division of Lawrence Berkeley National Labs. Lawrence Berkeley National Laboratory. He is formerly a postdoctoral research fellow. He joined LBNL when he was a postdoctoral research associate at He was a postdoctoral research associate at Montana State University Energy Research Institute in Bozeman, Montana. He was also affiliate of the postdoctoral research associate, graduate research assistant, and graduate teaching assistant at the Well Construction Technology Center of Mewborn School of Petroleum and Geological Engineering, University of Oklahoma. His diverse research experience in application theoretical, computational, and experimental methods to understand fundamental processes governing flow in the subsurface energy systems. His research interests include carbon utilization storage, methane and hydrogen storage, geothermal fossil energy resource development, and groundwater hydrology using advanced machine learning techniques, numerical models, and laboratory methods. Holds a PhD degree, petroleum engineering from University of Oklahoma, and a master's degree, petroleum engineering from African University of Science and Technology in Nigeria, and a bachelor's of science degree in mechanical engineering from the Federal University of Technology, also in Nigeria. He is a certified project management professional from engineering from the Project Management Institute. He was the SBE student chapter president and a SBE student chapter graduate liaison and graduate tutor at OU. He received multiple graduate awards and recognitions for his service and scholarship from the SBE and SAG. Well, without further ado, I'll go ahead and turn it over to you, to Dr. Omosebi, to go ahead and share your ideas, your presentation, and at the end, we'll have time for questions from the faculty and students.
All right. Thank you very much, Dr. Craig, for first inviting me and also for the introduction. I also want to thank Tracy Wilson for setting up this seminar. So the topic I'll be discussing this afternoon is on minimizing water loss in deep unconventional gas reservoirs, with the question that is surfactant effective for us to address these kinds of problems. So first, I would like to acknowledge the co-authors of this work, Dr. Tesu Tokunaga, who until his recent retirement is the PI for the project, and Dr. Jamin Wan is a co-author. I also want to thank Oklahoma Geological Survey and the Marcellus Shale Energy and Environmental Laboratory for providing us some of the samples that we used in our study. The project was sponsored by Department of Energy through the National Energy Technology Lab, but the views expressed here are strictly those of the authors and not of the DOE or NETL. So this will be a summary of the outline of my talk this afternoon. I will begin by describing the problem that we're trying to address, as well as the goal of the project itself. Then I'll go into issues that relate to water blocking, specifically the mechanism and the controlling factors for water blocking during hydraulic fracturing. And that is illustrated in the figure to the right. Let me quickly put on my pointer so that you can see my mouse. Yeah, so that is illustrated over here. Then I'll show some of the laboratory studies that we've done here. And finally, we'll address the elephant in the room: is surfactant effective at reducing water blocking? So if we think about the amount of water that we use on a per well basis during shale fracking, it runs into over millions of gallons of water. The cost of supplying this volume of water, as well as treating the flow back from the wells, they are quite large. They can run into millions of dollars per well. But the main issue is that not all of the water that is injected into the wells are actually recovered. A significant portion of the water, over 70% of it, stays in the formation and can lead to restrictions of counterflow of gas back to the wells. So thinking about a rational basis to reduce water use can be beneficial, both in terms of maximizing production, as well as conserving water resources. So the flow of fluids through a network of fractures is a very complex problem to understand, mainly because the properties of the formation, they are spatially and directionally distributed. They vary in different directions. Thus, we can never know the actual distributions of matrix and fracture permeabilities. So adverse effects of water imbibition into shales has motivated researching on ways to minimize water loss within reservoirs by manipulating, for instance, the interfacial tension, as well as mainly to manipulate the capillary forces. So we need improved and physically based models that are practical to optimize the use of water and for us to maximize hydrocarbon production. So for our project, the aim is for us to improve our understanding and predictions of water entry and distribution in low permeability materials, especially as shales. And we want to identify the factors that are controlling water blocking effect, as well as to improve simple models of water gas transport in unconventional reservoirs. So in order for us to achieve these set objectives, we first have to understand the fracture matrix contact area itself. It's a very important consideration for us to understand how water is lost into shale formations. So there are mechanistic models that basically assume planar fractures that are orthogonal to the direction of horizontal wells. But those kind of representations, they will represent the fracture matrix contact area. Complex fracture network models improve representation of fracture matrix contact area, but is there a way for us to learn from the amount of water that imbibes into a shale matrix, for instance, to give us an idea of how to estimate the effective fracture surface area? So we turn to imbibition analysis to provide us answers to that kind of question. So as we consider the mechanisms that lead to water loss in shales, so we say that leak-off of the fluid and imbibition is the principal mechanism that is responsible for water loss. But important questions for us to consider will include, can we reliably predict water loss due to imbibition into shales? And how does the imbibition scale with the permeability of the shales itself? And can we develop scaling relations to predict water loss and guide the use of water in unconventionals? And then the final question is, can we improve the direct measurement of water permeability in shales? So for us to be able to address this question, we'll take a look at the methods that are currently used for measuring permeability of shale, for example. Water permeability of shale samples, very difficult to accurately measure in the lab, mainly because the samples, if you've worked with shale, it's very difficult to do anything meaningful with shale in the lab. And because the samples have been distressed, as soon as they are recovered from the well and they undergo further damage during preparation for experiments. And so we see that shale permeability, generally, they're always stress dependent. So we try to use things like gas flow to measure permeability, and then we correct for slippage based on the clinking back effect. But those corrections that are needed to obtain the true permeability, they have inherent uncertainties. So other methods that a lot of people have used is to crush the shale samples and to obtain permeability from those samples. But that is not reliable because the rock matrix is destroyed as soon as the shale is crushed. Thus, it's eliminating intergranular flow networks that would normally have existed in intact shale samples. So now we look at the way to address this kind of problems from a practical point of view. So first, we begin by re-examining some of the classical works that have been done in the area of water imbibition into low permeable materials. So the Greenham's model expresses water block thickness at the local fracture surface in terms of permeability, viscosity, and capillary pressure, as well as imbibition time. And from that, we can develop this simple relation for the cumulative imbibed volume of water per unit surface area, so which is defined by I of T here. And that's just a product of the water block thickness, which is this L of T, L as a function of time multiplied by the water content in the shale formation. So what we see from this simple relation is that there are two terms that immediately jumped at us, and both terms have uncertainties inherent in them. One is the permeability of the shale itself, shown here in red, and the other is the capillary pressure at the advancing wetting front, which we refer to here as the P subscript C of F. So for us to be able to make anything meaningful out of this relation, the first thing we try to do is, rather than dealing with both parameters that have uncertainties inherent in them, which is K and PC of F, we would rather reduce the number of uncertainties to a single parameter, preferably the permeability in this case. So for us to do that, we have to go back to literature to look at data that have been published in terms of methane entry pressure. So we developed correlations between methane entry capillary pressure, which is what we refer to as PC of G here, and the permeability of the rock. And also we obtain correlations between the methane entry capillary pressure and the capillary pressure at the advancing wetting front. That's the PCG and the PC subscript F. So we obtain a correlation between those parameters from comprehensive database that we compile from independently published data. So, and by combining this relation between PC of F and PCG with the relations between PCG and the permeability, we're able to obtain a correlation between PCF, which is the capillary pressure at the advancing wetting front, and how does that scale to permeability of the formation. So, and the data that we use, as well as the feeds to obtain those correlations, they are shown on the right. So now, if we go back to the equation from Greenham's model, and we substitute the relation for this P C of F, which is now just a function of one uncertain variable, which is permeability, then we can obtain an equation that scales permeability directly to the capillary pressure at the advancing wetting front as water imbibe into the permeable material. So going further, the effective permeability can be expressed in terms of sorptivity. In the petroleum engineering literature, we're more familiar with subtivity being termed as fluid loss coefficient. So in other literatures is referred to as subtivity, and that's what is referred to as S here. So we can develop a correlation that relates the subtivity to the permeability, such that from a simple imbibition experiment, we can measure the subtivity of a given shale specimen and then use this relation over here to estimate the permeability of that particular shale formation. So to test that subtivity-based prediction of K, so we compiled literature values of permeability and the subtivity from sources where both K and S were experimentally determined on the same materials. And the value of K we calculated using these simple relations compared to the measured permeability actually compare favorably, as you can see here on the concordance plot. So looking at fluid flow, so from a fluid flow perspective, the factors that control water blocking, and Dr. Horn from Stanford, they have published different papers on this particular subject. And you see from some of the models that they've developed from that research group that water blocking is mainly a function of formation-dependent parameters, which are listed here, as well as fluid properties, which are listed in interfacial tension, wettability, viscosity, and relative permeability. In addition to that, shorting practices, in other words, things like shorting time and shorting pressure, those are important considerations as well. So, but the controllable parameters really for us is mainly with the fluid properties, because most of the formation properties are not things that we can easily manipulate. So, and the model that was presented by the Lee and On paper that I referenced is just showing here, for instance, how water block thickness depends on capillary pressure, for instance, where if you had things like surfactant, which is mainly reducing the capillary pressure, then you can reduce water block thickness. And the other way, or the other things that we can try to do in the lab is to add a fluid thickener, in other words, to increase the viscosity of our fluid as a way to minimize the water block thickness. And we actually explored these two ideas in the lab. So where we added guar, that is a major component added to fracturing fluid, just to see how increasing the viscosity of the fluid will minimize the amount of water that imbibes into shale formation. So we experimented with Eagle Ford Shale, and the result from our experimental study is shown on the right. So the first plot here is showing the cumulative imbibed volume of fluid, in this case, thickened fluid with guar added, versus time. And then we generated the same plot now with plotted against the square root of time. And the linear portion of the plot is where you estimate the subtivity for that particular sample. So what we see is that as soon as we add guar to the solution as expected, the increase in the viscosity of the fluid did decrease the subtivity of the sample. So that's, goes along with what we expect from theory from Dr. Horn's work from Stanford. So with water, we observed that cumulative imbibed volume per unit flow area increases initially up to during the first 40 days of the test without stabilizing, and that's what is shown here in the blue curve. But with guar, it flattened just after about 20 days of the experiment. So, and the subtractivity reduction itself is about 73% with addition of guar. So adding guar or making the fluid thicker will minimize water block. But from a practical point of view, the viscosity of the fracturing fluid has to be specific in terms of the propellant carrying capacity, as well as the fracture geometry that we're trying to obtain. So we really don't have a window of manipulating that as a practical option to minimize water block effect. So we have to look at other options. So another option is to add surfactant, which has been encouraged by a lot of surfactant proponents, people who have conducted research and have advocated for the use of surfactant. So indeed, adding surfactant to fracturing fluid will reduce the capillary pressure that drives imbibition, thereby decreasing the thickness of the water block zone at the fracture matrix interface. So, and there are, of course, other use of surfactant beyond minimizing water imbibition into rocks. Things such as forming microemulsion and altering wettability to facilitate oil mobilization, for example. So, but our interest in this study is to look at gas reservoir to see whether or not adding surfactant can minimize imbibition of water into a deep gas formation. To demonstrate that in terms of laboratory experiment, that indeed surfactants will minimize imbibition of water. So we conducted a spontaneous imbibition experiment using Marcus Shale with and without surfactant. And the results is what is shown here. So the fluid itself without surfactant, here's the surface tension. After adding just 0.02% weight percent of surfactant, we did decrease that slightly. And now using that fluid, that's the fluid without surfactant and with surfactant, and conducting imbibition experiments with the two sets of fluid shows the result that is indicated here. So what we observed is that the cumulative imbibed volume of water per unit area is actually reduced with surfactant added to the base fluid. But that is with a caveat. The caveat there is that that is in a laboratory experiment, which a lot of people have actually demonstrated. And in most cases, it's always with surface conditions with regards to temperature and pressure. So indeed, using surfactant helps to minimize water block effect. But the question is that sustainable under reservoir pressure and temperature conditions? So as we go deeper in the well, the surfactant that demonstrates good reduction of water imbibition at the surface, will it be that effective at depth? So for us to address that question, so we begin with a conceptual model that depicts how fracturing fluids are distributed shortly after hydraulic fracturing. So the this view over here is showing a kilometer scale overview of multiple hydraulic fractures within a single fracturing stage. And the next figure here is showing the meter scale depiction of the region that includes hydraulic fracture and things like natural and stimulated fracture, where frac fluid has been supplied via the main hydraulic fracture. And then the other figure here shows a millimeter scale close-up view of water imbibing into shale matrix from a vertical hydraulic fracture and a secondary horizontal fracture here. So you see actually that the water block thickness is orientation dependent. So if you have a vertical fracture, you have something that looks like this, horizontal fracture, and then you have something that looks a little bit different. So the data that we have available have shown that in the days that follow fracturing and just prior to production from the reservoirs, with matrix permeability that run from nano to micro Darcy range, the imbibition front itself only propagates within a few centimeter, a millimeter to centimeter into the rock matrix. So when such short penetration distances are small relative to the distance between fractures themselves. So if you have a cluster of fractures, if you have the distance that the fluid is imbibing into the matrix for a particular local fracture matrix interface, if that distance is smaller compared to the distance between the fractures, then water imbibition occurs locally as effectively a one-dimensional process that emanates from a complex fracture networks. So we can represent that with a simple one-dimensional model to be able to predict the water block thickness. So at the local scale of shale matrix adjacent to the fracture, as we supply fracturing fluid, so the pressure difference between the advancing wetting front and the fracture matrix interface itself is essentially going to be the summation of the pressure at the fracture matrix interface and the capillary pressure at the advancing wetting front, which is what I indicated previously as this PCF that we've been able to scale with permeability. So after rearranging and integrating classical Darcy equation for a 1D flow, and we can obtain this relation that essentially mimics what has been published or shown before from the Greenham's model. And if we express the cumulative imbibed volume of water as a function of the water block thickness, being so I of T being the product of L of T and the water content, which is indicated here as delta theta. So we can obtain the relation for the cumulative imbibed volume of water per unit flow area. So our focus here in this particular equation is to examine the significance of potential changes to PCF, particularly in comparison to this variable we define as PO, which will be the the pressure at the fracture matrix interface. So the relative magnitude between these two parameters will determine the importance of surfactant addition in terms of reducing water imbibition, because what surfactant addition we essentially do is to reduce this PC subscript P, that's capillary pressure at the advancing water front, PCF. That's what the addition of surfactant will be manipulating. So we focus on the relative importance of these two parameters, looking at laboratory measurements as well as considering field scale conditions. So looking at the equation that I showed previously, that's the L of T, which is the water block thickness. So given that the absolute value of the capillary pressure at the fracture matrix interface exceeds the capillary pressure at the advancing wetting front during fracturing, so we can simplify that particular relation to the equation that is shown here. So the figure to your right over here is plotting this simple relation as a function of permeability. That's three different orders of permeability, and then looking at how shortening time impacts that. So what we see from this top figure, for example, is that water volume per unit entry fracture pressure is actually less than about 1 centimeter if you look at just about 30 days after shorting, you have a water block thickness that is about 1 centimeter into the shale formation. And similarly, water block thickness for a microdarcy range permeability, they are just about 1 centimeter thick for shorting up to a month. But that can have significant effect on production if you consider the interconnectivity of fracture network area. So, and the cumulative imbibe volume, we observe that it actually increase with time. So minimizing shorting time is will be a good practice to minimize water block when it comes to reducing the amount of water that imbibes into the formation. So looking at the relative magnitude of the capillary pressure at the advancing wetting front and the pressure at the fracture matrix interface, so we can determine what is the driving force for imbibition. So the capillary pressure at the fracture surface, which is the PCO, as we define over here, is actually constrained within 2 parameters. So the upper end is the breakdown pressure or the frac pressure of the rock. That's shown here. And this depth, pressure, and temperature plot. So that is the green line over here. That's the max. And then is the lower bound is the reservoir pressure. So essentially the pressure at the fracture matrix interface is within those 2 limits. So at a depth of about 2 kilometers, if we consider a shorting capillary pressure at the fracture matrix interface of about 30 megapascal, and we look at a 1 nanodarcy material, so the absolute value of this capillary pressure at the fracture matrix interface is about 9 times the capillary pressure at the advancing wetting front. And this is obtained from the relations that I showed earlier that we obtained for the PC subscript F as a function of permeability. So we see that indeed the capillary pressure at the fracture matrix interface is more of a dominant force than the capillary pressure at the advancing wetting front, which is what surfactant is mainly added to alter when we add it to fracturing fluid. So PCO therefore is more dominant than PCF, especially for low permeable materials. So for us to have a better picture of how the surfactant will perform as we go deeper into the well, so the next step for us is to be able to estimate how PCF itself, that's the capillary pressure at the advanced wetting front, varies with both depth and K. So we already have a correlation for how it varies with permeability, but then that all those experimental data that we used to develop this correlation, they were all obtained at surface condition. So for us to be able to obtain PC subscript F as a function of depth and permeability, so we have to determine how the methane water interfacial tension varies with depth below the ground surface, because that is what will account for the depth dependence of PCF. So we obtained a relation for the depth dependence of the methane water interfacial tension from the literature over a range of pressure and temperature combinations that are compatible with this particular plot that is shown here. So we're looking at temperature within this range and pressure within this range. So we obtained this correlation for methane water interfacial tension as a function of depth. And if you, at the surface, for example, Z would be 0, and then you essentially have interfacial tension to be 72 millinewton per meter, which is the value that we have at the surface. So this relation, therefore, is used to scale the capillary pressure, that's the permeability-dependent capillary pressure at the advancing wetting front at surface condition, to the interfacial tension that is more depth dependent. So we therefore have this strong permeability-dependent PCF, which also depend on depth, and is shown here as plotting the PCF as a function of depth to see how it varies for the three different orders of permeability that we're looking at: millidarcy, microdarcy, and nanodarcy. So you'll notice from this particular relation, for example, that it differs slightly from the popular Levert scaling function, where you have the power to be 0.5. So, and that is to show again that Levert scaling, it's not particularly applicable to shale materials, and that's from the data that we have available in the literature. So as a result, the depth-dependent cumulative imbibed volume per fracture surface area will take this particular form, and that's from the relations that I've shown previously. So we therefore have this cumulative imbibed volume of water per unit flow area that depends on depth and also depends on other fluid properties that we have in the equation originally. So we can use this relation to understand the effectiveness of surfactants. This term, for example, here, this term F, is a fractional term that indicates the fractional reduction of the interfacial tension at whatever depth we're interested in, and how that is impacted by addition of surfactant. So if I start with interfacial tension at the surface of 72, and I had surfactant that reduced it to, say, 50 or 58, for example. So the ratio between those two numbers will be the value of F, and I can use that in this particular relation to determine whether or not surfactant is indeed effective at the depth of interest. So we define, for us to answer that question, what we did is to define what we call the capillary alteration effectiveness, CAE, and what it represents is the effectiveness of hardening surfactant just for the sole purpose of reducing water imbibition. So this figure to the right shows the depth dependence of the capillary alteration effectiveness for three orders of magnitude of permeability for millidarcy, micro, and nano darcy at three different fractional reduction in interfacial tension, and that's the term F that I described previously. So the three groups of the fractional reduction in the interfacial tension that we've shown here represent a modest reduction of interfacial tension from adding surfactant, and then the 0.01 here represents a very strong reduction, and then the -1 really represents the maximum possible case where you have extremely strongly hydrophobic formation, essentially. So we wanted to see that for these different values of possible reduction in the interfacial tension, will surfactants still be effective as we go deep into the formation? So the plots here actually shows the result from this capillary alteration effectiveness plotted versus depth. So what we see is that surfactant alteration can indeed be more important in low permeability materials, as we can see for nanodarcy material. For example, shales, because in shales, because of the very tiny pores, you have higher capillary pressure at the advancing wetting front. So adding surfactants can really be effective for that relative to the high-end permeable materials. However, as we go deeper, what we see is that the capillary alteration effectiveness decreases with depth, irrespective of the order of permeability that we're looking at, mainly because the pressure at the fracture matrix boundary becomes too large and becomes the dominant driving force. So therefore, contrary to what has been published, that surfactants are effective, yes, they are, as we've shown from laboratory measurement, which is mainly surface condition. And you can see over here actually, so at the surface, we have all the curves, approaching 1 to indicate that the addition of surfactants is indeed effective. But as we go deeper into the formation, the story change gradually. So the shallow limit of the zero depth indicates the laboratory type of measurement that we have in the lab. But at depth, we have a different story. For example, capillary alteration effectiveness will diminish to only about 10%, where we have all of the curve intersecting this particular red line. So therefore, a more practical option to consider when it comes to minimizing water block, particularly in deep gas reservoirs, will be to minimize shutting time, as well as to consider reducing shutting pressure. So in the interest of time, so that we can have time for question, I will summarize. So what this work has shown is we develop practical relations for predicting imbibition characteristics and water permeability in low permeable materials. And we show that we can constrain actually the wetting front distance is constrained to about 1 centimeter scale into the shale matrix. And using surfactant and thickened fluid did show that yes, we can minimize water block at surface condition. For thickened fluid, we are constrained because we really can't add fluid thickener to the fluid beyond what we can pump, for example, and also what may not necessarily be needed to carry propant and to suspend them in the fractures. But for surfactant, we at the surface condition demonstrated by both our lab experiment and also the simple analysis that I just described. Surfactants are indeed effective at the surface, but at depth, as we go deeper, more practical options to consider will be minimizing shutting time and shutting pressure as viable option to minimize water block effect. So that will be the end of my talk. And these are papers we've published on this from this particular project, addressing different issues relating to water adsorption as well as meeting adsorption into shale materials. So I'll be happy to take questions.
Thank you very much, Dr. Omosebi. We really appreciate your presentation here today. I wanted to give an opportunity to our students to go first. Do we have any questions from our graduate students? All right, don't be shy. Any questions from graduate students?
I still consider myself a student anyway.
We all are, right?
Yeah, we all are.
All right, questions from anyone, faculty or students? Dr. DiCarlo.
I have a question. Very nice work. I'm going to say your name wrong. How do you say it again?
Just call me Tayo.
Omotayo. Omotayo. Very nice work. Yeah, so the did you look at basically surfactants getting stuck on the rock also? I mean, I don't think the surfactants do much actually. I mean, again, I think your main result that the pressure is so great that the capillary force is not imbibing much is relevant. But did you also look at basically surfactant retention in the porous media or no?
No, we didn't look at that in terms of our experimental work, but we believe that because this analysis is not just from our work, it's also from other independent laboratory work that has been conducted. So we're not sure if that will have any impact on the conclusion that at depth, using surfactant may not necessarily, be the way to go.
Okay.
Other questions? Any other questions, faculty or students?
Yeah, I have a question.
Dr. Delshad, please.
Yes, I know, I guess Dr. DiCarlo also mentioned that maybe surfactant is not that effective, but just curiosity, if they were effective, how would you decide what is the optimum capillary pressure reduction or interfacial tension reduction before you go to the field or before you do your experiments?
Well, perhaps the way to decide that will be that relation for, so this particular relation, for example, so you can design the surfactant in terms of the amount of surfactant you want to add to the frac fluid and estimate, for example, let me put on my pointer. So estimate, for example, this fractional reduction that you can obtain and use that in this simple relation. The closer this parameter or an index is to 1, the more effective the surfactant you're about to use will be at the depth that's where the fracture matrix interface is essentially. So you can use this simple relation to have an idea of how effective that surfactant would be. Again, this is based on data we have available in literature. Okay, so perhaps we'll learn more with more data, and it will be interesting to hear from folks that have field perspective in terms of adding surfactant, because I've watched recently some SP videos where adding surfactant has been advocated, but do we have evidence that indeed the surfactant is effective in terms of minimizing water imbibition? Now, the work here should not be interpreted to say we should not use surfactant, because of course we use surfactant for different purposes depending on the kind of problem that we're addressing. But for a specific problem of minimizing water block in shale, shortened time and well-shortened pressures are perhaps more practical in terms of having a more meaningful effect than surfactant.
Well, thank you. That was very helpful. But do you generalize your results to oil shale?
To what?
To oil?
No, so
your focus has been on gas, but
correct.
What would be the role of surfactant for oil?
Oh, to be useful, right? Surfactant, is very, very useful to mobilize oil. That's a different problem to consider, right? So for that purpose, surfactant perhaps will be more useful, but if it's for gas reservoir, that is where this result will be more applicable.
And then my last question is, what is the role of wettability here?
Right, so wettability, we actually consider it. I mentioned that, so here although I didn't show it in this relation, but we actually use the Young Laplace equation, which is more for a straight tube and not necessarily applicable for porous media, but it gives us an idea of what is the maximum effectiveness that we can obtain if we have an extremely strongly hydrophobic surfactant, for example. So, and that is where you have essentially that cos theta being 90 degree, that's wettability angle here. That's what will represent this negative one. And the result here show that even for that, you know, the surfactant addition, as we go deeper in the reservoir, is not really that effective. Of course, we obtained some, we achieved some minimization, but it diminishes depending on the depth that we're looking at.
So basically, the readability is captured through contact angle.
Contact, correct, yeah.
Okay, all right, thank you very much.
Thank you very much, Dr. Delshad. Any other questions from the group?
I do have one question. What do you think of the other argument that more shut-in time is perhaps or can work to mitigate the water block from oil production or from gas production point of view, in the sense that the water will be kind of smeared, and then it will, the more time you shut in, the more favorable the conditions are for gas to be produced back. What do you think of that argument? Yeah,
it depends on the pressure, you know, that you have left in the reservoir to push out that water, right? If you don't have enough pressure, you know, to push back that water will remain in the formation. And that explains why we have about 70% of water remaining in the formation post-fracking. So because that water is going somewhere and it's not coming back to the surface.
Yeah, I got it. I guess I meant, yeah, in terms of water loss, for sure, if you shut in less, you will recover more water, right? But I'm thinking more of the conditions for the gas production. So if you're really not considering much your water loss and you're more concerned about the gas production, then you are concerned about the water loss. Would you be thinking more shut-in time or less shut-in time?
For production, again, depending on how much pressure is left in the reservoir. If you have very low pressure, perhaps less shut-in time is the way to go.
Got it. Thank you very much.
Thank you.
Dr. Torres-Verdeen, did you have a question?
Yeah, quick question. Omotayo, excellent presentation. Thank you so much. I imagine there's a lot of work behind the scenes for your presentation, so it goes without saying that we're very impressed with the amount of work that you showed. But I wanted to ask you, in your studies, did you look at the chemistry of water and how it affects the imbibition of that you talked about here?
From the lab experiment that we have conducted ourselves, no, we didn't, because it would be nice actually to have, you know, formation water with all of the chemistry in there to use to see how that will impact the results that we have. So we have not really considered that in what we've done so far.
Yes, you know, I was asking that question because among some practitioners, there's this idea that the chemistry of the water that is collected after production is typically not the same as the chemistry of the formation water. And the differences cannot be explained just by the differences between the water that is used for hydrofracking and the formation water. So I was wondering if this process of hydrofracking actually breaks up some of the bondings that other water perhaps is stored tightly because of nano confinements and that sort of thing. And that was the reason why I was asking you about this chemistry of water.
Yeah, that would be interesting to, yeah, in terms of the chemistry. I know that's a little bit complicated, and from our standpoint, it's not something that we've really looked at as far as that will impact how much water will be retained from experimental point of view. For instance, we've not looked at that.
Yeah, I think that some of these surfactants, or the effectiveness of these surfactants, probably it's in some way tied up to the chemistry of formation water, I would think, right? Because of these joint forces, double layers, and things that often are microscopic or nanoscopic, but they have a big effect on the overall picture.
Right. Yeah. Now, things like, double layer effects, osmotic pressure effect and stuff like that, how the samples are, the condition of the sample when the experiment is conducted itself will determine what kind of result you expect. So for example, in most of this analysis, the samples are not confined, you're just exposing the samples to water imbibition under unconfined condition. So the effect of those kind of mechanisms might change what we have, but we don't have enough data out there to give us a better picture of the impacts of those kind of effect on the results we have accumulated.
Thank you. Thank you so much.
Thank you.
All right, Tayo, thank you very much for spending the time with us and discussing. Appreciate your efforts in building this presentation. And when we're back to normal, we have to have you come and join us and visit in the 40 acres here in Austin, okay?
I look forward to that.
Awesome. All right. Thank you very much, everyone for attending. Stay safe.
Thank you. Happy Thanksgiving, everybody.
Okay.
Thank you. Normal. What is normal? Do we know anymore?
Hey, Masha. Yeah, well, at least having people in person.
Well.